Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to show you how to set up a ship model using an OBJ mesh input. We're also going to explore some nonlinear hull excitation to look at some parametric roll that happens with this particular ship model. So you need to make sure you have the sample project files that includes this specific folder, KCS, downloaded from the ShipMo3D website, extracted on your computer. We'll go to ShipMo3D and open project, go to KCS. KCS stands for KRISO Container Ship vessel. And the KCS is, it's not a real ship, but it's designed particularly to be susceptible to parametric roll. And we'll take a look at that after we load some of the ship properties in a little bit closer detail. So first we're going to go add existing data, panel hull, open the file. Now note, unlike the other projects, we are using a wavefront OBJ input file. So we'll pick, what you want to do is pick KCS hull.obj. ShipMo3D loads only half of the mesh and then automatically mirrors it across the midline. And we just go save and then run. Go plot panel hull. So you can see how there's quite a lot of detail here with a bulbous bow and a bow flare in the front, as well as a lot of stern overhang. And based on the ship properties that we've got right now, there's also some automatic mesh refinement along the waterline. Even though we provided the mesh by OBJ file format, which is good. That works really great for numerical conditioning. Both the stern overhang and the bow flare are really crucial to be able to see these effects of parametric roll. And you have to be able to have some kind of method of nonlinear loading and wave excitation and buoyancy loads as well to see parametric roll happen. So you need to have that full mesh as well as the mesh above the waterline is what I mean. So next up we have panel lid. This is optional, but we can still add it. Make sure we're specifying files in our local project folder. For the wet panel hull we just made, go save, run. It goes pretty quick. We'll plot panel lid. It looks good. Looks like a good fit along the waterline and the interior. This will be helpful at suppressing any irregular frequencies in the radiation and diffraction calculations. So next we go to rad diff. It's the next application, and we want to make sure we're picking the wet panel hull file we just generated in our project folder. Same with the lid that we just generated in panel lid. We're going to leave all these other properties the same. Just note that if you do want to investigate any potential for parametric roll, you do need to make sure you're covering cases that will line up with the excitation frequency properly. So generally what you want to be looking at is a forward speed that gives you that encounter frequency that's near the roll natural period of the vessel, but that's already been kind of established and set up. So we'll go save, and we're going to go run, and this will take some time. So we'll come back and check on this in a while. So it's been some time. We've gone through the radiation and diffraction calculations, and we'll go, just as a matter of course, plot the radiation and frequency-dependent added mass and damping values. You can see lots of smooth curves here, maybe a couple little divots here that might be related to numerical conditioning, but generally it's pretty smooth. So go to the next step, add existing data, build ship. And we'll make sure we're selecting the radiation diffraction database file, the dry panel hull file there. There's a rudder and a propeller already set up that are pretty basic. So save and run this. is just going through an iterative calculation to resolve the RPM necessary to figure out the forward speed, associated forward speed. So if we go plot ship now and take a look at the ship model, we can see the wet mesh in yellow and the dry mesh in green. And at this trim, we're right. Note at this trim, you can very clearly see where if there's any changes in wetted hull area, there's going to be quite drastic changes. It's very sensitive at this area, especially at the stern overhang, and that's going to be key for checking out what happens in with a nonlinear model in FRIMO. So there's also the rudder and the propeller that we've added to the ship model. So we need to have a seaway set up to use with FRIMO in the maneuvering analysis. And there's an existing seaway file that's made, but I just want to show that you can create your own using build seaway. Build seaway is a very basic application, and it just gives you a chance to set up, regular or a spectrum, and a few other options here for resolving the ship motion. So we can save this and run it and see some of the characteristics under view output, but for now we'll just leave it like that. Next we're going to go to FRIMO, the time domain tool for maneuvering. And this is where we need to also make sure we're specifying the ship motion database in our project folder that we made in build ship. And we've got an option. You don't have to have a seaway, but we have to if we want to see parametric roll. So we'll select our seaway here, and this is going to be in a head wave condition. But everything else should be set up correctly. Now, one thing is if this is key for watching parametric roll. Your nonlinear hull force model option has to be buoyancy for Krylov, or also alternatively buoyancy for Krylov wet area. Both of them do the same thing. The nonlinear loads scale a little bit better with the wetted area option. It's really up to you. Linear, everything's linearized about the wetted area, the draft hull wetted area, and you won't be able to see any parametric roll effects unless you have nonlinear selected. Note there's some initial roll here. We'll just start that off at 0, and our set maneuver commands have it just running at a steady forward speed, and we'll save this and run it. Now this is the linear calculation, so I don't expect to see any effects happening here, and you can see it just goes straight up into the waves, and if we go plot displacement, in particular in roll, nothing's happening. There's a heave motion following sinusoidal response. Just to be really sure, we can initiate this with sort of like a 1 degree roll, it's a very small value. And sometimes particularly non-linear models might need an initial perturbation to get going, but again, this just decays out with linear calculations. Now, if we change it from linear to buoyancy for Krylov, for example, and run, it takes a lot longer because it's a more in-depth calculation, resolving the forces based on each panel, each wetted panel. But if we go plot displacement, you'll see a little bit of noise, and then after 400 seconds, you're getting that build-up of parametric roll, reaching almost 20 degrees. So parametric roll is a nonlinear effect that happens when the encounter frequencies affect stability parameters at a rate close to the natural roll period, and that's really what we're seeing is effectively a roll resonance effect. You got to get the nonlinear options working if you want to see it. So hope that makes sense. Thanks for watching.